Most people think Mars is a dead planet, dry, frozen, lifeless. End of story. Today, buried beneath its surface, there is enough liquid water to cover the entire planet 1 mile deep. And that's not even the strangest part. The strangest part is what we found on the way to figuring that out. Every great investigation has a mantra. In a rain-hammered city, a private eye following a trail of crime and corruption lives by one rule: follow the money, follow the numbers, follow the transactions. And if you are dogged enough, you eventually find the truth. When it comes to Mars, scientists have a different mantra: follow the water. The case they are trying to crack is one of the oldest cold cases on record. One that has baffled investigators for centuries, possibly millennia. Did life ever arise on Mars? And like all good investigations, it comes down to collecting the right evidence. Because if water once flowed on Mars, the sediments it left behind might carry something far more valuable than minerals. They might carry signatures of life itself. Find the water, potentially find life. The detectives assigned to this case are unlike any who have walked a beat before. They have steel in their hearts. They almost never sleep. Their memories are literally photographic. We call them rovers. And today, we are going to walk through the moments they blew this case wide open. The discoveries that, one by one, upgraded our understanding of Mars from might have had water to something nobody was prepared for. Not just rivers, just lake beds, oceans, beaches, tides, and liquid water that still exists right now, kilometers underground, waiting. This is not a simple story. It took decades. It required 3 separate rovers on 3 separate continents of Mars. And it ends in a place that will reframe everything you thought you knew about the Red Planet. But we start, as all good investigations do, at the beginning. December 15th, 2010. Sol 2449 of the Opportunity rover mission. Let's put that in perspective. Opportunity was designed for 90 days. It had been rolling across Martian soil for nearly 7 Earth years, far beyond any mission guarantee, far beyond what any component was rated to endure. Some of its onboard motors had already failed. It could no longer stow its own robotic arm, and yet it kept going. By this point, Opportunity had covered over 25 kilometers, crossing flat plains, threading through sand dunes, examining bedrock, peering into craters. It had found chemical traces, suggesting certain areas were regularly flooded. Hints of water's ancient presence scattered through the chemistry of rock. But not one single piece of conclusive, undeniable proof that sustained liquid water had persisted in any one location. Opportunity needed something better. And on the horizon, finally, something better was waiting. The Mars Reconnaissance Orbiter had detected clay minerals inside a massive 22-kilometer crater called Endeavour. Clays are hydrated minerals. They cannot form unless liquid water has been present and stable over extended periods. Not a flash flood, not a brief puddle. Real, sustained pooling liquid water in contact with rock. Opportunity turned toward Endeavour and drove. On Sol 2709, Opportunity arrived at the rim of Endeavour crater, at a section called Cape York, at a point named Spirit Point, after its sister rover, which had died on the other side of Mars only months before. Opportunity had now travelled over 30 kilometers, 50 times its original planned mission distance. And from the first moments at Cape York, it was clear this was somewhere different. The terrain changed. Peaks and ridges rose against the horizon. The bedrock was older, exposed at the surface, accessible for analysis. No more smooth plains, no more endless dunes. Mission controllers, said the Endeavour region, gave the mission the equivalent of a second landing site for the price of one. The first major rock Opportunity examined was a large ejecta fragment, Tisdale II. Unlike anything studied before on Mars, volcanic in origin, unusually rich in zinc and bromine. Scientists determined it was a breccia, old rock fragments fused together. The chemical signature pointed to water. The impact that threw Tisdale II had likely released hot underground water that deposited minerals as it cooled. But Tisdale II was not the discovery. The discovery was a few meters away, hiding in plain sight as a thin white line. Look at the rock outcrop. Look at the base of the image. There, barely visible, easily missed, is a pale white vein running through dark rock like a scar. approximately the thickness of a human thumb, easy to overlook. Opportunity's alpha particle X-ray spectrometer analyzed it. Calcium, sulfur, together calcium sulfate, gypsum. They named it the Homestake deposit. Gypsum does not form in dry conditions. The only way this vein could exist is if water once dissolved calcium out of nearby volcanic rock, carried it through an underground fracture, combined it with sulfur, and deposited it as calcium sulfate into that crack, which was only later exposed at the surface by erosion. This was not surface water. This was not a flood. This was water flowing through underground fractures on Mars. Slow, chemical, geological. The kind of water that soaks through rock over long timescales and leaves its chemistry behind like a signature. But there was something else. Something that elevated this above every previous water-related finding on the planet. The Homestake water had been neutral pH, not the harsh, highly acidic sulfur-rich water inferred at Opportunity's original landing site. Not corrosive, not hostile to biology, neutral, chemically mild. The kind of water in which life does not merely struggle to survive, it thrives. For the first time, Mars had offered proof not just that water existed, but that water of the kind that could support life had once moved through the Martian crust. Opportunity had cracked the first lock on this case, but the deeper vault was still ahead. After a Martian winter sheltering at a sun-facing slope called Greely Haven, confined to one area, analyzing rocks to stay productive, Opportunity emerged in the spring and continued its circuit of Cape York's rim. The Mars Reconnaissance Orbiter had indicated clay minerals somewhere ahead. The team was determined to find them. On Sol 357, a rock outcrop came into view. The microscopic camera found something unexpected. Smooth, rounded formations embedded inside the rock, similar to Blueberry's Opportunity had seen years before, but smaller, only a few millimeters across, not iron-rich. Directly fused into the rock rather than sitting loose. Some had been eroded away, exposing their internal structure. Scientists described them as crunchy on the outside, softer in the middle. Different in concentrations, structure, composition and distribution. A new mystery, a new open question, a new reason to keep going. A short distance further, Opportunity reached the clay patch it had been hunting, Whitewater Lake. And there, in the pale outcrop at the top of the image, a rock about the size of a human forearm, sat the treasure the mission had been building toward for 9 Earth years. Esperance. Testing confirmed what the orbiter had only suggested. Esperance had a clay mineral content produced by intensive alteration by water. Higher in aluminium and silica, lower in calcium and iron, more dramatically altered than anything Opportunity had ever examined. Clay minerals of this kind only form when rock is soaked in water, not briefly, not occasionally, but consistently and deeply over geological timescales. Opportunity spent weeks at Esperance, running every test available, making sure every measurement was confirmed. When the data was in, the best evidence from any Mars mission that neutral pH water had once sustained contact with Martian rock long enough to fundamentally alter its chemistry. Water that was not just present, water that was by every standard of Earth's own biology habitable. 9 years, 30 kilometers of Martian desert, one forearm-sized pale rock, and the case was just getting started. 2021, Jezero Crater, a new mission, a location chosen specifically because orbital data suggested it was once a lake with a river delta flowing into it. One of the strongest surface candidates for a place where life might have once existed. Within the crater, a dune field called Seta contained a series of outcroppings exposing multiple geological layers, each layer a different era of Jezero's history. Access to them required crossing sand dunes that had killed the Spirit rover in 2009. So before Perseverance attempted the crossing, NASA deployed something entirely new, Ingenuity, a small helicopter. The first powered aircraft ever to fly on another planet. It scouted the route from September through December 2021, flying at 10 meters above the surface, mapping every dangerous patch of loose sand. Perseverance followed the scouted path to the outcropping known as Brack, and then the rocks delivered a plot twist nobody expected. Scientists had anticipated sedimentary rock, the classic signature of lake floor deposition. layers of fine particles settling in still water. Exactly what you'd hope to find on the floor of an ancient lake. Instead, igneous rock, olivine, formed by cooling magma, not sediment, volcano. The initial reaction was something close to disappointment. Magma doesn't support life. An igneous crater floor doesn't tell you about ancient lakes. Except, look more carefully. The olivine showed unmistakable signs of water erosion. The ridges at the crater's edges showed evidence of water flow. The volcanic activity had come first. The water, the river and lake that built Jezero's famous delta, had arrived after the rock had already cooled. And here is the part that flipped the entire interpretation. Igneous rock, once cooled, is enormously mineral-rich. This is why volcanic soils on Earth are the most fertile on the planet. Add mineral-rich volcanic rock to a sustained supply of neutral liquid water, and you have, by every measure of Earth's own biology, near-ideal conditions for the origin of life. The volcanic rock wasn't bad news, it was the best possible news. Perseverance began drilling, collecting samples, sealing fragments into titanium tubes. One of those samples, NASA would later describe as the clearest sign of life ever found on Mars. That sample is still sitting on the floor of Jezero crater right now, and we may not hold it in human hands for decades. While Opportunity and Perseverance were working craters on opposite sides of Mars, a third rover was doing something historically unprecedented. July 2020, China's Tianwen-1 mission launches. The name means questions to heaven. Aboard an orbiter, a lander and the Zhurong rover. On May 14, 2021, the lander touched down. China became only the second nation in history to successfully deploy a rover on Mars. But it was where Zhurong landed that changed everything. Utopia Planitia, the largest known impact basin in the entire solar system. Long hypothesized as an ancient ocean floor, a 2016 NASA study had found a massive reservoir of underground ice in the region, roughly as much water as Lake Superior, locked beneath the surface. But nobody had ever sent a rover to ground truth this. Zhurong was the first. Using its ROPAR ground-penetrating radar, Zhurong began scanning below the Martian surface, sending radio waves down through the soil and measuring where and how they bounced back. The team encountered 76 geological reflectors, boundaries between different underground materials. What stopped them cold was not that signals bounced back, it was the angle. All 76 reflectors sloped in the same direction, at angles between 6 degrees and 20 degrees, not scattered in multiple directions. Not random, all pointing the same way toward the lowlands. Mapping the data revealed a 1.3-kilometer stretch of terrain sloping toward lower ground, buried 10 to 35 meters below the surface. The team compared it to Earth and found a strikingly close match: the Bay of Bengal, a classic foreshore environment, the zone between high tide and low tide where ocean meets land, where sediment accumulates in angled layers shaped by waves and tidal action. One co-author said it plainly. It's a simple structure, but it tells you there had to be waves, there had to be a nearby river supplying sediment, and all these things had to be active for some extended period of time. Mars did not just have lakes. Mars did not just have river deltas, with beaches, with waves, with tides. And Zhurong had just found one. Buried underground, preserved for billions of years, waiting to be discovered with radar instead of a shovel. We now have water in underground fractures, clay minerals altered by sustained neutral water, olivine eroded by water in a mineral-rich volcanic crater, a buried coastline in an ancient ocean basin. The water was everywhere, real, sustained, and then it was gone. How? Between 3 and 4 billion years ago, Mars underwent a transformation that permanently changed its fate. Its global magnetic field collapsed. On Earth, our magnetic field is generated by the slow churning of liquid metallic iron in our outer core, a planetary dynamo that creates an electromagnetic shield around the planet. That shield deflects the solar wind, the constant stream of charged particles blasting outward from the sun. Mars had such a field, then its smaller core cooled faster. The dynamo weakened, the field died. Without the shield, the solar wind began stripping the Martian atmosphere, particle by particle, year by year, millennium by millennium. Atmospheric pressure dropped. The greenhouse effect failed. temperatures plummeted. Liquid water at the surface became unstable, it evaporated, and much of that vapor was swept away into space. What remained froze, locking into polar caps, permafrost, shallow subsurface ice. The warm, wet Mars of 3 billion years ago became the frozen, airless desert of today. But here is the problem that drove scientists quietly mad for decades. Even accounting for everything lost to space, everything frozen in the caps, everything locked in the shallow subsurface, the water budget does not balance. The known reservoirs are not large enough to explain the rivers, the lakes, the deltas, the oceans. Something was hiding, somewhere. Something was holding a vast reserve of Martian water in a place nobody had thought to look. The answer was not on the surface, not in the polar caps, not in the shallow permafrost. It was in the crust itself, buried between 11.5 and 20 kilometers below the Martian surface. Locked in fractured igneous rock with every crack, every fracture, every void filled with liquid water. We know this because of NASA's InSight lander, a mission built not to explore the surface, but to listen to the interior of Mars itself. Over its 4-year mission, InSight detected more than 1,300 Mars quakes, seismic events from meteor impacts and internal volcanic rumblings. Each quake sent waves rippling through the planet in every direction. And the key to seismic waves is this: the way a wave travels through material depends entirely on what that material is. Waves move differently through solid rock than fractured rock, differently through dry rock than water-saturated rock. The speed changes, the pattern changes. Scientists applied mathematical models of rock physics, identical to those used on Earth to locate underground aquifers and oil fields, to InSight's seismic data. The data could not be explained by dry rock. It could not be explained by ice. The only explanation that fit was a layer of fractured igneous rock, with its cracks completely filled with liquid water, a reservoir so vast that if it was somehow brought to the surface, it would cover the entire planet of Mars to a depth of 1 to 2 kilometers. Liquid, not frozen, not ancient. Liquid water right now, under Mars, today. The water did not all escape to space. It did not all freeze. A significant fraction went deep, sinking into the fractured crust as the surface dried out, finding its way into the warm, pressure-stabilized mid-crust where liquid water can persist indefinitely. Mars is not a dead world. Mars is a world whose water went underground, but answering one question opened another, and this was still wide open. If Mars had liquid oceans billions of years ago, rivers feeding coastal deltas, waves breaking on beaches now buried under Utopia Planitia, then the ancient Martian climate must have been warm enough to sustain liquid water at the surface for extended periods. Here is the problem. 3.5 billion years ago, our sun was approximately 25% dimmer than it is today. Climate models consistently predict that an early Mars under a fainter sun with its early atmosphere would have been frozen, not wet, and yet the geological evidence says it was wet. This is the faint young sun paradox, one of the most persistently embarrassing unsolved problems in planetary science. 3 competing theories attempt to bridge the gap. Theory 1. Mars was warm and wet. An atmosphere loaded with greenhouse gases, CO2, water vapor, possibly methane or hydrogen, was dense enough to trap sufficient heat for sustained liquid water. But models suggest CO2 and water vapor alone cannot do the job. The additional gases needed are chemically unstable and hard to maintain long-term. Theory 2. Mars was only sometimes warm and wet. Volcanic eruptions and asteroid impacts periodically released heat and greenhouse gases, creating brief warm spells where ice melted and rivers ran. But we cannot confirm whether those events were frequent and intense enough to carve all the valleys and fill all the lakes the evidence suggests. Theory 3. Mars was cold and icy, with occasional melting. Orbital changes or sudden heating events periodically melted the ice, allowing brief periods of liquid flow. This explains both glacier evidence and river channels, but struggles to account for sustained ocean conditions and deeply water-altered clay minerals. None of these 3 scenarios cleanly explains everything. In December 2025, a paper published in Communications, Earth and Environment found evidence in Perseverance's clay data suggesting those clays had been sculpted by consistent, heavy rainfall, tilting the scales slightly toward the warm and wet scenario. One paper, one dataset, one more piece of a puzzle that has resisted completion for decades. Solving the faint young sun paradox may be the master key to understanding whether Mars was ever truly habitable. Not just intermittently wet, but warm enough, stable enough, and long enough for life to take hold and persist. We do not have that key yet. Here is the cruelest part of this story. Everything we have found, the gypsum vein, the clay minerals, the water-eroded olivine, the buried beach, the underground ocean, points toward one conclusion. Mars had the conditions for life. And somewhere inside Jezero crater, sealed in a titanium sample tube drilled from mineral-rich, water-altered volcanic rock, sits what NASA described as the clearest sign of life ever found on Mars. Not a vague chemical hint, not an orbital signature. A physical sample, collected by Perseverance, sealed, labeled, and placed in a cache for retrieval. The Mars Sample Return mission was supposed to bring it home. Planned for the late 2030s. The most scientifically significant retrieval operation in human history. In 2025, it was defunded. Congress secured NASA's broader budget in early 2026. But the Mars Sample Return was the one program that did not survive the cuts. Not for scientific reasons, for budget reasons. The kind of decision made in meeting rooms, by people who will never have to explain to the future why they chose not to find out. The clearest sign of life ever found on Mars is sitting in a crater tens of millions of kilometers away, sealed, waiting, with no confirmed plan to bring it home. It may be retrieved not by a robotic mission, but by the first humans to walk on Mars, planned for the 2030s. Astronauts in spacesuits who will need to travel to Jezero crater, walk to the sample cache, and simply pick it up. If that happens, the moment will be unlike anything in human history. Not a data point on a screen, not a spectral graph. A scientist in a spacesuit, standing on the floor of an ancient Martian lake, holding in gloved hands a tube of rock that may contain the fossilized remains of something that once lived. You started this video thinking Mars was a dead planet. Now you know what the evidence actually says. Let's close every loop we opened. We followed the water with opportunity, across 30 kilometers of Martian desert, to a thin white gypsum vein called Homestake, proof of neutral pH water flowing through underground Martian fractures. Water that could have supported life. We found Esperance, a forearm-sized pale rock in a clay patch at Endeavour Crater's rim. 9 years of mission. The best evidence at the time that sustained neutral liquid water had fundamentally altered Martian rock chemistry at the geological level. We crossed the dunes with Perseverance, guided by the first helicopter ever to fly on another planet, to olivine bedrock in Jezero crater. Volcanic rock, water-eroded in a mineral-rich environment, near-perfect conditions for life, samples sealed. One of them, possibly the most important object in the history of science. We landed with Zhurong in Utopia Planitia and found a buried shoreline. 76 geological reflectors sloping uniformly toward the lowlands, angles matching Earth's coastal foreshores. Proof of waves, tides and rivers meeting the sea. Mars had oceans, Mars had beaches. We listened with insight and found a liquid water reservoir 11.5 to 20 kilometers deep in fractured igneous crust. Large enough to cover the planet a kilometer deep. Still liquid, still there, right now. We confronted the faint young sun paradox, the unresolved question of how a dimmer young sun allowed liquid water to persist on ancient Mars. 3 competing theories, no clean answer. A December 2025 rainfall paper that hints but does not confirm. The master key still missing. And we sat with what remains stranded. The clearest sign of life ever found on Mars, sealed in a titanium tube in Jezero crater, defunded into indefinite waiting, perhaps to be retrieved only when the first human boots touch Martian soil. The case is not closed. The private eye is still in the rain-hammered city, still following the trail. But here is what we know now that we did not know before. Mars is not a dry, dead world. It is a world with a water history longer, richer, and more complex than anyone imagined. Rivers fed coastal deltas. Oceans had beaches. Tides rose and fell. Water altered rock chemistry into conditions where life could have taken hold. And somewhere deep in the fractured crust, that water is still there, cold, pressurized, liquid, patient. The evidence is in the ground. The evidence is in the tubes. The evidence is in the seismic waves. All of it pointing to the same thing. Mars had everything life needed. We just need to go there and look. Follow the money, find the criminal. Follow the water, find the life. We followed the water all the way to Mars. Now we just have to go there and finish what the rovers started. Thanks for watching. See you in the next one.